Okay, I'm Abel Vesa. I'm working for Linaro for almost 2 years. I'm doing kernel work for Qualcomm platforms. Been doing some kernel hacking for almost a decade now. Upstream maintainer of the NXP IMX clock drivers. I did some kernel bring ups for Qualcomm and NXP as well when I used to work for them. And lately I've been working on upstreaming the latest compute platform from Qualcomm. During this last couple of months working on the bring up basically, I realized that I need some kind of a fast way to boot kernels, test stuff, and then also boot on remote platforms, remote boards, because some of the time you wouldn't have access to the platform itself. So yes, but we didn't have that there either. So then we had like, we wanted to have fastboot, obviously, not to install any kernels via deb packages or something. Wanted to be able to boot to fully fledged distro by the time we had like a display working, GPU and stuff like that. I mean, it has to be like, had to be pretty easy to set up. So using pre-built rootfs images and initrd images helps a lot in this case. It's not perfect, it's still work in progress. It can be improved. It was built over time, so any suggestion is more than welcome. Basically, from the whole cycle, we want to spend most of the time on hacking. I mean, we can't do anything about the building of the kernel, but everything else should be as short as possible, from my point of view at least. Why? Okay, I've heard some like pretty good excuses of why you wouldn't want to test something on a board for somebody else, because it like I have to do the setup, I have to like if I can't reproduce it on the first boot, then I have to do a lot of booting. I don't want to build deb packages. I probably want to have all the modules installed, or I want to build the modules as built-in, just to not have to append the modules to the initrd or anything. Also, when it comes to end-to-end testing, until recently I haven't had a way to actually test fully fledged Debian, but booting over fastboot. So this is where basically the setup came from. Obviously, you don't need any kind of distro installer. You can use the pre-built images, as I said, and the ease of remote access to the target is also necessary if we're working more than one engineer on the platform at a time. So I've split this into three major steps, let's say, and before going to each one of them, we should probably have a look at how the boot flow looks like in comparison to the mobile platforms. So we're probably used to mobile platforms, Qualcomm platforms, booting via fastboot. But when it comes to compute platforms, we don't use ABL. It usually comes with Windows Boot Manager. So we kind of have to do some kind of setup initially on with respect to the partitions and the rootfs and stuff like that on the storage, NVMe in this case. Then I'm also going through the step of how to build a proper boot image and appending all the modules, firmware boot scripts, and testing tools. So it becomes faster when it comes to like booting the board, rebooting after you test it. So, and then at the end, I'm mentioning the tool that we use in the Qualcomm lending team a lot, CDBA. It's really great for remote access. Basically does that over SSH. I'm going to go to that at the end. So, boot flow on mobile platforms. Keep in mind, I'm not an expert on boot flow. I'm just doing this for to get around to test my kernel. So, usually on the mobile platforms, you have the primary bootloader, and then which is usually fused into the chip fabric, as far as I understand. Then it jumps into the extensible bootloader, which kind of brings up the rich execution environment. There's also a secure one, but I'm not going to go into that. And from there, it's Android bootloader, which for us, in our case, we want to have fastboot protocol, so that brings us that. At the end, it shuts down the boot services before jumping into kernel. So, and this is how the Android world looks like from kernel hacking point of view, at least. On the compute, everything is the same up to XBL, same as mobile, but here we have something called Windows Boot Manager. In this case, so in case of compute, you can specify which EFI app to load via the EFI boot options and the boot order. If you don't specify anything, or if you're trying to boot from USB, for example, I think it will just take the boot ARM64 EFI. So you can do the same setup on USB, and if you rename whatever EFI you want as boot ARM64 EFI, it should be booting that. The problem with obviously with the Windows Manager is that it doesn't provide fastboot for us, so we want that. In order to do that, we have to add a new EFI app in between the XBL and the boot manager. So that's where grub or systemd comes into place. It allows us to chain load EFI apps, so we can still boot to Windows if you want. It allows us to load DTBs, kernel initrd, supports most of the popular partitions, let's say, but I'm suggesting ext4 because I think that module is already built in the core image, I think, of the grub, so you don't need anything else. Or at least vfat is for boot options, for a boot partition if you want, but I suggest skipping the boot altogether, just going straight with the root partition. And it's highly configurable to some degree. You can actually build in some of the modules, so you don't have to go through having a grub config folder. And I mean, you could also install it via the distro tools, grub install and stuff like that, but I suggest you don't try that on a platform where you're trying to bring up. Also lacks fastboot implementation, which we're still aiming for. So it allows us to boot Linux. You can have like that nice menu entry with lots of different kernels, DTBs, and stuff like that. But what we're interested in is having fastboot, which is again, a EFI application. You're not going to be able to have access to that yet. I can say that somebody in Qualcomm is working on having that open source, but yeah. Yes, so we want fastboot, that's the point.
Can you explain why you want fastboot?
Yes. You would want, after you build your own kernel, you want to not have to do any kind of steps.
Don't you have to wrap it in a boot image?
Yeah, but that's like...
well, I'm just wondering, because like you have grub there, so if you have networking support, you could TFTP the kernel and not have to do that step, right?
Yeah, but that doesn't work for remote access.
What do you mean, like, anyway, we can get into that then.
Okay.
Interested.
So setup of the partition layout, basically. Usually, since it's a compute, comes with the EFI system partition. We're going to call that the ESP from now on. It's VFAT. It needs to be EFI partition because the EFI doesn't. It's not able to load anything from any other type of partitions. So it kind of needs to. Okay, then you have. You can load any EFI apps there. Again, comes already there because you have Windows. And then you also, if you want to boot to proper root, you would have to have the root partition created. So X4 is what I would aim for because, again, grub supports that pretty well. And if you want to boot the kernel, load the kernel and the DTB and initrd from there, it's working well. So it also acts as a boot partition, so you don't need to like a different one. But for systemd boot, for some reason you still need the boot partition to be xboot LDR type, at least for now. I'm focusing more on grub because I mean I managed to get this running pretty fast, and but it should be the same principle basically. Grub. So you install it. Well, you basically copy it in under the EFI or anywhere basically on the EFI partition, and then you modify the boot option to point to that. You can change the boot order as well to have that on the first position, so it actually boots to grub. Two things to mention here, the root and the prefix. So grub relies on these two to point to the partition where it's supposed to load the kernel, DTB, or chain load EFI, other EFI applications. So root specifies that partition, and then the prefix is used to point to the grub directory, which can be on both EFI or it can be on the proper root, whichever works. There's also a term of early config file, which is basically an embedded one, so you can pre-build the grub with a small configuration file, let's say, that allows you to set those two variables. So you can point to something else. And usually if you take a pre-built grub EFI from a different system and you try to boot with that, if it points to the wrong partition, you're not going to be able to boot. So it just drops you to rescue. So that's a bit of a, that's what the grub install tool does for you. It actually changes the prefix and the root for you. So it also allows, obviously, loading pre-existing DTBs, kernels, images, and initrd. You have a nice menu again. And we want, again, to have fastboot EFI chain loaded from it. Some of the commands that are probably important to mention here. So if you want to boot the kernel from the storage itself, then you need to specify the device tree because it's an ARM64. You need to specify the kernel image, and you need to specify the initrd image, basically. Chain loader allows you to chain load, basically, other EFI apps, and boot is the, let's call it, start command for whatever you chain loaded or loaded via the other commands. So, and then normal is also a module, but it's also one of the modes. So if it ever drops you to rescue, it's because it cannot find whatever the root and prefix points to. So in order to go to the normal mode, you would have to set those up from the grub rescue shell, and it would allow you then to run the normal command, which takes you back to the normal mode, basically, where you have the nice menu entry, whatever. Grub make standalone is a tool that basically allows you to, let's say, build a grub EFI with modules in it. So you can specify what modules you want to have supported, like X4 or normal or other things like that. And it's like a mem, it's called mem disk image, basically. So puts everything into one EFI app. And then grub install is the one that usually is run when you install the grub from the distro point of view. So yeah, I'm against that because I've heard about situations where it messes up stuff. So I would rather do it by hand. Sorry. Oh. Yeah. Fastboot and shell EFI. I'm going to talk more about the fastboot because that's what we want, but shell EFI is useful for when you want to change, for example, boot options, boot order, you want to copy or rename files, and you don't have proper OS to do that, or the only thing you can do is boot to some EFI app. So that's where the shell EFI helps. The fastboot EFI is the one we want. You can add a grub menu entry for that, and a boot option if you want. So you can bypass the grub altogether. It boots Android boot images, and I'm going to go through that later on. Well, building the boot image. So we want to have an initrd image, which Linaro provides in the snapshots, is Yocto based, I think. You can boot to that without any root kernel argument, and you don't need any kind of storage support. So if, for example, you're trying to bring up the board, you're not having NVMe or something like that, you're still able to reach shell and do some stuff from there just with the initrd. If you want to boot to proper rootfs, which can be either on NVMe, USB, UFS, whatever, also there are pre-built images, Debian images, that you can take from snapshots. You have to specify the root device as a kernel argument. Obviously, storage support is needed, otherwise you're not going to be able to boot to it. And one hacky thing is, I would like to mention here is that if you ever want to have the modules being copied from the initrd to the proper rootfs, you need to kind of hack the scripts local bottom copy extras. That's a script that you can add on your own and copy after the rootfs has been mounted. The reason you would want to do that is because otherwise you would have to boot at least another time just to copy the modules. And we're trying to avoid booting multiple times just to install a new kernel or modules. So it can also be repacked, unpacked, repacked if you want to add stuff to it. But the best thing about it is that you can append different CPI-RGZ files. Like, for example, modules can be a different GPIRZ file that can be appended, firmware, testing tool, whatever. Yeah. I'm trying not to get into much detail. Building the Android boot image. So make boot image is used for that. We usually use the header version 2 because otherwise you don't get the DTB segment. And then you have to append the DTB to the kernel image, I guess. Yes. You also, if you use header version 2, then you can pass a different argument DTB and then point to the DTB you want to use. You pass on the kernel image base for the entire image, and then page size, kernel arguments, initrd, and then obviously the output image. Just a note there for the command line arguments. Specifying, so currently on Qualcomm platforms, I would argue that you need at least the PD ignore unused and clock ignore unused just to make sure that it doesn't shut off display or whatever before you reach the desktop environment. Yeah, next up is CDBA. So CDBA is a wrapper around SSH, I would say, with a client-server architecture that allows you to have like multiple boards controlled. Usually, so I mean, we use it a lot for Qualcomm platforms, which come usually with Alpaca debug boards that allow you to power on, power off, and other things. I think it also supports USB control relays. I don't know if, yeah, okay. And for the server side, once you build it and install it, you have to set up some udev rules, because otherwise you wouldn't be able to open those TTIs. The CDBA config file specifies per each board the GPIO configuration and fastboot device ID and whatnot, basically, for each platform. And then at the end, you need to have, like, if you want to give access to somebody else, they need to give you the SSH key. So obviously being over SSH. And then the client, once you build it and install, all you have to do is pass the host name of the server, and then the board you want to boot, and then the boot image at the end, and you should be good to go. I actually do this even locally, so I have like the board next to me on my desk, and I'm still using CDBA because I don't have to worry about powering up and powering down the platform. So all I have to do is run just one command, brings me to prompt, run the tests, then there's like a keystroke, control AQ, I guess, and shuts down the device. So, and it works well for sharing we have a couple of such servers in the Qualcomm landing team, so yeah, we use that a lot. Yes. I wanted to show this, but unfortunately I'm not able to connect my own laptop. So if you want to see this, we can probably showcase it at the demo on Friday. Yeah. Here are some references, and I guess, yeah, questions. Yep.
Hi, so in the slides you went through the mobile boot stack and the like desktop server boot stack for Qualcomm boards. What is the long-term plan as regards the Qualcomm boot stack on automotive boards?
What is the long-term?
What are the long-term what's the long-term approach to the boot stack on Qualcomm automotive boards? 'Cause the automotive boards are very close. They're somewhat closely related to these boards.
I don't know how the automotive is supposed to work, but I have Srini here.
So the automotive boot chain looks completely different to what we are trying to do here. The automotive boot chain looks completely different to what we are trying to do here. I can't go into more details of how it looks like, but it's totally different to what mobile and compute platforms in general look like.
I had one more question. There was one slide you had up as regards the Windows boot stack, and it looked like in the slide that Windows got booted via system D. Okay, no. I think it was the next slide.
You can actually boot system D as well.
But if you buy the board as, say, just a consumer, like a standard board,
Windows laptop.
Windows,
So it's basically
it would be like this. Okay, yeah. Yeah, makes sense. Sorry. My bad, I misinterpreted.
Any other question? Hey, present time. Oh, sorry.
I think I already know the answer to this, but you could use CDBA on any system. It's not Qualcomm specific.
Yep. Yes. To be honest, I would like to see that outside of Qualcomm as well. Yeah. It's completely open source as far as I know. So, yeah.
Even the hardware.
Not the alpaca one. Okay.
So I was thinking about the TFT, so the netboot argument. So what is the advantage of using fastboot over the netboot?
Yep. Thanks.
May I steal the microphone and answer this question? The first advantage is that you don't have to copy your images anywhere. You just from the build directory, you run fastboot, or you run CDBA or any other tool, and so you just get it into the device. And second point is that not all devices are connected from the beginning, and during the bring up, we cannot heavily depend on having the network. So the bootloader, the boot chain usually supports booting through fastboot, well, thanks mobile or thanks Android, and then we are just reusing it heavily and dependent heavily on that.
Yeah, less of a question, more just an additional clarification that the motivation to use fastboot is because we already had CDBA and already had this working for embedded Android boards and Android phones, and it's easier to port fastboot to the new laptops than it is to come up with some other mechanism and implement it on both the laptop and the and CDBA, as I understand it.
There's also, like, if you use the TFTP, you'd have to have, so you'd copy, obviously, the kernel image, whatever, initrd to the server, but then you'd have to load, I'm not sure it's better than the fastboot, to be honest.
Also, it requires an additional binaries on top of UEFI to get the image either through TFTP or, sorry. That was the second. Yeah, and also it requires an additional binary, additional bootloader to work on top of UEFI, well, which gets bigger and bigger, and the whole chain also gets bigger. So, for example, the alternative, one alternative approach uses the Pixie boot to load all the kernel, all the stuff onto UEFI-enabled boards, but the boot chain becomes really big and dependable. Yeah. But this also works without grub.
You talked about those two boot arguments, right? That clock ignored boot arguments, which you said that it should be enabled on all the dev boards for...
Oh, the clock and the PD.
Yes,
yeah.
those two boot arguments. So whenever we try to enable those on our devices, we get a pushback that fix the kernel. So what is the upside of enabling those two arguments, and what will happen if I don't enable those boot arguments?
So I think there is a late init call that basically disables all the clocks, in case of clocks, that are not used by any consumer. And the same thing applies to the PDs. And if you have clocks that have been left on, but they're not assigned, or if you load the module later on that would be the consumer of that clock, then the late init call would cut the power, for example, for display. So you wouldn't be able to have display working until basically ever until you have the module loaded.
So is it device-specific thing that on certain devices I should have these arguments on?
If you're using kernel modules, then you need those flags, and that's something we need to fix. But I mean, it's a shortcoming. We will turn off any clocks that might be in use for and not yet picked up by a kernel module. And in our case, we have several IP blocks that just hang if we do that. So yeah, so several people report that it works fine for them. That is, it might look like it's working. It might be working. Yeah, it's all warranties off. So, but this is a thing we need to fix in the upstream kernel. How do we deal with clocks that are on from boot up until a point where a kernel module is loaded later?
Yeah, so just one last quick addition expanding on the previous answers. Ideally, you would not have any of those, but some developers are less strict than others in their testing, let's just say, and some resources are not described. So even if in ideal conditions where all of the modules are either available or built in, the resource dependencies may not be fully described. So Linux will think that, for example, this power rail is not necessary to drive the display, but in reality it is. And once Linux disables it, because again it sees it as unused, the display goes black.